Hello everyone, it's Kevin here again, and this week we're going to be covering APIs, Application Programming Interfaces. So at the high level, they just serve as a communication protocol for devices to send data between each other. So the server, for example, and the client. We're going to go over a couple pretty important concepts here. So HTTP, REST, HTTPS, TCP, OSI model, and APIs. Now with the OSI model, there's a caveat. We're just going to kind of go over the layers that we're going to use. So I'm going to try to go through this quickly. Probably isn't going to end up that way, but we're going to try it. Also, my hand's messed up. It's in a cast, but shouldn't affect this. So to begin, the API, right? That's the end goal after all this stuff is the API and how we can use it. But so yeah, you might as well know what the API is. So API, just a little bit of terminology here. It's Application Programming Interface, and it's essentially a structure that lives on a server, a program you could call it, that serves data, right? So we use HTTP as a protocol to, structure that data. We use JSON or XML to structure the messages, the data itself, right? Because there's multiple layers to that data. So you have like headers, you have your request, and a whole bunch of other stuff. But at the high level, right, it serves as a complete system for communication. And some areas where it'd be used is we might have a server. So server here, we might have a couple of clients. So the clients are the consumers, those that consume the API, and the server is the one that's serving the information. So the server could be out in the cloud, or it could be on premises. It could be somewhere living, like it could be in my basement running, set up port forwarding on my Wi-Fi or on my router or whatever, and bingo, there you go. You can do all that stuff. But typically nowadays you're going to see a lot of cloud solutions. So what this API can serve is, it can serve as a framework for you to communicate between the client and the server. So the client, 1, 2, 3. A good example is like weather data. So this client, you have an application. Let's kind of try it out here. Sorry for the noises. And we have like time here, and I don't know, whatever other stuff up here. And we want to display some weather-related information. So Monday, Tuesday, Wednesday. Let's just leave it at that. And the high, right? The high is going to be 70. Let's just say, for example, the low is going to be 55. So on and so forth. So you're going to display this data on the screen, but this data has to come from somewhere. So where do we get this data from? From the server. And of course, with weather-related data, we have to send some information with that. So we might want to get the data for a certain zip code. So we'd go and send a request to the server and say, hey, server, give me the weather-related information for the next 5 days. So period, time period, 5 days, zip code, 56362. Let's just say that one. So we're going to go ahead and ask the server to send us our information for this, for these here parameters. And the server's going to be like, hey, cool, here's the information. And the information might be, oh, that's terrible, curly brace, but for period of 5 days, zip code 56362, it might say for Monday, you're gonna have a high of, I'm running out of space here, high of 70 and a low of 55. Now this isn't gonna be actually how it's structured right exactly, but kind of give you an idea of how that would move back and forth. We're gonna go over serialization and deserialization as well here later on, but for now this is what matters. So for Monday, here's the information. Then for Tuesday, so on and so forth. So it's just going to continue like that. And that data is going to move back and forth. Go like this. It serves as that framework, right? So that you can communicate. So with HTTP, that's kind of the core of it, the hypertext transfer protocol, HTTP. hypertext transfer protocol. There's a little bit of structure to it. I have some notes here just so that I can give you some accurate info. So basically, this message that's being sent back and forth has to have a little bit of information. So to begin, we're going to have our method. So we could have like post method, a get method, put, delete, update, or whatever. There's a whole bunch of different types of methods. I focus on gets and posts just because those they're so versatile, right? So you can do so much stuff with them, and we'll go over why. But basically, we have our method, we have our header, and we have our body. And our method is, of course, a get or post, all that stuff that I mentioned. It has to be one though, right? So for this message, it has to be one method. Our header or headers, they're going to contain some information relevant to that session. So the message that's going back and forth. So for example, we're going to have our host. So the host is the website that we want to go to, or the URL. What is it? Universal or uniform resource locator, something like that. We're going to have our user agent, so a little bit of information about the device that's going back and forth. So you can have like iPhone 10, whatever, or Safari. Typically, it'd be like more like browser related info, because you're not going to go and send a request directly from your iPhone, right? You're going to go on Safari or whatever. Or if you're doing it from an Android, you might go from Chrome. So it'll send some information related to that. And if you ever on like a website and you get some spam, and it's like, oh, your iPhone 12, right, has a virus or whatever. How do they know what phone you have? It's because of that, the user agent. And the accept is the payload type. So you could have like JSON or text, or it could accept a file. Some examples. And I forgot to mention probably the most important part about the header. You can set your own headers. So I personally do this with APIs that I write. So if I want to go back and forth with some data that I want to have consistent with the header, because the reason you want to do this is because it's stateless, right? HTTP is stateless. It doesn't care where the message is coming from. So this message could come from mobile application. It could come from a Chrome browser, Firefox. It could come from wherever that could send that request, right? It could even be a curl request or whatever via the command line. So if you just do curl, like for example, www.google.com, I'm not going to write it down, but if you try doing that into your terminal on whatever device that you're on a Mac or Windows, it's going to return that information for that whole site, what that would respond with. So it doesn't care though. That's the point where it comes from. So we can use that to kind of pass session related information back and forth. So once the API does get this message, this request, it could be like, oh, it's coming from an iPhone, or it's coming from a tablet, right? Whatever. And you can program for that. So there's a couple different versions. We're not going to get too deep into that. We have like version 1, 1.1, and then I believe 2. And those just add functionality. Eventually get to a certain point where you can do like two-way communication, and that uses like webhooks, a whole bunch of other complex, relatively speaking, structures for communication. Just maintaining an open connection. So for example, like let's say we have an API that serves messages back and forth. I kind of want to make sure that you guys all have an idea of what I'm talking about. So we have our user 1, user 2, and our server. User 1 sends a message to the database, to the server. The server goes and updates the database. And user 2 sends a message, and user 1 wants to know when that message is sent. Without any sort of open connection, what they would have to do is they'd have to sit there every 1 second, 2 seconds, 500 milliseconds, whatever, sending requests like, hey, is there a message inside of the database for that, that table, or for a certain ID? Hey, is there hey. So over and over again. That's called polling, when you go and send messages without caring about what the result is, essentially, without knowing, I think is more important there. And that, of course, can really be taxing on the server. That open connection can allow user 2, for example, here to send that update to the database table. So for for conversation ID, whatever, store this message. And then the server is going to have a system in place to say, hey, user 1, the message was updated. And then user 1's going to have some logic, typically, just sitting there waiting for something to come. Boom. Once the server says, hey, the message was received, it'll go and fire off that logic under user 1. It's kind of complex stuff. Signal R is a good example if you ever want to look into that. It's a really cool system that can offer that two-way communication. But for now, it's not super important. Then we have a REST, right? REST, representational state transfer. And what this does is it serves as a system of like guidelines or like a protocol for, it's typically used with HTTP. It doesn't have to be, but it's typically used with HTTP in conjunction with that. And that serves, it kind of lays that framework of get, post, put, delete. And they essentially serve for CRUD operations, CRUD. There's a reason I write code and not write on a whiteboard for a living, but CRUD, so create, read, update, delete. They kind of correspond. They're not necessarily one-to-one, so you could create something with a post. You could create something with a post. You could also create it with a get if you really wanted to. You could read with the get. You could read with a post. You could update with a put or with a post. Delete with a delete or with a post. So there's a lot of flexibility, but typically if you want to have an API that's easy, it really helps with route maps essentially. And if you have an API that you're sharing with people, so hey, here's my API for my database that has messages or whatever. So Facebook has this API, just theoretical, they might not. And this API can be used to serve information to any client, any device that wants to send that request. They can send out a route map and say, hey, this route here, get users for ID, get users for ID X. Right, that's going to serve as, like in the name states, get users. And I think I've covered already before in the course to use descriptive names for all this sort, not just like get you or something like that, but get users for IDX. And this is what's going to be used in the site. So for example, Facebook. So for example here, HTTP, facebookapi.com, we're going to go into HTTPS in a little bit, but let's just assume HTTP for now. There's some Facebook API, right? This is the URL, and we want to go and access get users for IDX. You could write, based on this facebookapi.com, you could write a route map, which says what each one of these routes do. So you don't have to see the logic itself, because this get users route probably exists in some controller. If they use C#, it'd be like some controller. Flask, they could be using Python, right? Or they could be using Node. It doesn't really matter, but you don't have to see the logic though. This is pretty straightforward. Get users, and get users for what? For IDX. So essentially what the route map does is it can take this endpoint, this API, the endpoint is actually the endpoint, right? With all of this stuff where you're going to go and access that specific information for that specific route. But you can take the URL and it'll go and write out all the routes that you can call, and whether they're gets or posts or puts or deletes. And right away, if you see get users and it's get, all right, you're getting some information. You're getting a resource from the server. Post user, async, maybe, right? It's posting a user asynchronously. Delete user for IDX is going to go and delete that user for that ID. So really helps that sort of stuff. Up here to make some more room though. So the big ones though are get and post, right? Because they're so flexible. And the big difference between these two is how that data is sent back and forth. So with get, for example, you might have HTTP myapi.com / get users. So how do we transfer this data? So say the client right here, the phone. How do we structure that data so that they can send it via the URL? We do $ID equals 1. That's how we would do that, right? And this, of course, can come with the potential problem that if you're sending sensitive information like a social security number or anything like that, anybody can read this. Anybody can click on that URL or intercept that request and, oh, cool, like we have that message, right? So we have that, or not that message. It is a message, right? But we have that structure, so it's get. We have our headers. We have our body. Those query string parameters, which is what these are called, the query string parameters, are passed in plain text. Unless you hash them, unless you make them, unless you encrypt them, basically. And if we have this information moving back and forth without encryption, that can be a huge risk for users, especially if you're passing sensitive information back and forth. Now, with post, what post will do is it'll just be, I should have gotten rid of that, but HTTP myapi.com post user. This is not a very descriptive name because what are we posting, right? What are we actually doing there? We're not. Create user might be a better one, so let's just say create user, honestly. That would be a little bit better. Create user. We don't have any information going back and forth in the URL. So it adds a level of obfuscation, whatever, of hiding that information. Now, of course, if you use Wireshark or any other system to go and intercept those packets that are moving back and forth, you're going to expose it, right? So it's still going to be exposed, but it helps hide it a little bit, right? So a non-tech savvy person, if they click on the URL, they just see the information right there. That's a huge risk right there, of course. Non-tech savvy or a tech savvy person could go and intercept that body if it's not encrypted for a post request, but again, it adds a layer. That's good when we don't want to have our information leaked. Puts and deletes, I don't use a whole lot, but put can be used for like updating something, so updating a user, and then a delete for deleting a user or deleting a resource on the server. Okay, so at a very high level, that's what HTTP is. What is HTTPS? HTTP and REST, by the way. HTTPS takes these concepts together, so the Hypertext Transfer Protocol, REST, and a little bit of encryption, not a little bit, a bunch of encryption, and it makes these messages, these systems secure. So let's say we have some clients, just 2 clients, honestly, would be good enough. So say user 1 wants to send a hidden message to user 2, and this message might be like, here's a routing number, here is a checking account number. It's not, realistically, that's not what you're going to be doing, but you get what I mean. Or maybe a hidden message that you don't want anyone else to see, I guess. So it can be super flexible. If that message goes out to the server, because if you think about it, it essentially has to go through the server, because if we have, it seems like I'm going over a ton of stuff, but we have the earth here, just a whole section. We're not going to just use radio communications typically because we're affected by the curvature of the earth. So user 1 is here, user 2 is here. They send that message. They're limited to line of sight, right? So they're limited to like right there, which is like what, 13 miles, I believe, something like that. So what we do is we use these servers. So we send the data to via a wire essentially, or wirelessly. So if you have like a router set up that's going via wire, right? So it could be fiber optic cable, or it could be any other type of cable, and that could go to your ISP. Then that gets transferred throughout the entire world. Or you could have another system where you have satellites up in the sky, and then that way you don't. I don't know, I got rid of that, but you have that satellite. Like that. The user goes boom to there. Satellite here. Boom. User here. So that could be an example, right? But yeah, realistically, we're not going to go straight from user to user. So how do we encrypt this information going back and forth? Because if the server could intercept it, they could be storing it, and this information could be used for malicious purposes. It might not. Honestly, most of the time, the vast majority of the time, it's not used for malicious purposes. The problem is that somebody goes and hacks into that server, or maybe they don't have strong, secure protocols in place to prevent people from hacking into the server. All this data can be leaked. The databases can be leaked. I'm sure all of you have heard of companies that have like passwords stored in plain text. Then boom, it's data breach, and now the passwords are out. What happened? Well, it's not that the server was doing anything maliciously. It's just that they were incompetent, right? They didn't encrypt stuff, or maybe they didn't encrypt it strong enough. They weren't in the loop essentially with that kind of stuff. So what we can do though is we can use HTTPS, and it's a really, really cool structure because it uses asymmetric encryption. So the way that this works is, without that, we go and send that message out to the server, and then user 2 over here goes and gets that message, because actually, let's just assume that we have a communication protocol where once user 1 goes and updates something in the server, user 2 is immediately notified and they read it. So that message makes it to user 2. If anybody intercepts it here, now they have access to that, which is bad. We don't want somebody doing that. So what we can do is we can use what's known as, like I said, asymmetric encryption, and we have what's known as a public key. So let's just call this PU, okay, 1, and we have a private key, so just PK1. Then we have another public key and private key pair here, PUK2 and PK2. So what we can do, and something important about these public and private keys is that a message encrypted with a private key, so for user 1, if they encrypt a message with their public key, they can decrypt it with their private key. And if they encrypt a message with their private key, they can decrypt it with their public key. Really important. It's two-way, and that's really important with data integrity or data authentication. So you can be sure that whoever sent that message really sent it, not somebody pretending to be them. So I have some notes here. So let's say, for example, this user wants to go and send a message to this other user. What this user will do is they'll encrypt the payload. So they'll have that message, and they'll encrypt it with this public key. So now the message that they sent, so they took a message and it's going back, over to the server, and it's going to go to user 2 now. If somebody intercepts that message, the public key, as the name states, is public. Anybody has access to it. But they can't decrypt, right? They have to use the private key to decrypt something signed with a public key, something encrypted with a public key. So if somebody gets access to it, that doesn't matter. It doesn't, because it's essentially, I'm gonna ignore the big elephant in the realm of quantum computation, and the whole cryptographically, or the whole post-quantum algorithms and post-quantum encryption stuff. Just for what we're going to be doing here, it's not really relevant. So if somebody gets access to that with current systems in place, it would take millions of years to decrypt it, to go and brute force your way through it, and just brute force where you attempt a whole bunch of passwords. So boom, 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 just millions per second, and eventually you get the right one. But as that password length increases, I don't know if you've ever used those, if any of you have seen those websites where you can test how strong your password is, and it'll tell you how long it takes to crack it with a modern processor. So it's essentially, I don't want to say it's impossible, but it's really difficult to get to the message. So when you go and encrypt the message using their public key, they get the message and they decrypt it with their private key. Then again, back this way, if the user wants to go and send a message this way, and they want the user wants to be able to decrypt it, they encrypt it with the user one's public key, and then they can decrypt it with their private key. So this is it's a really robust system currently. The thing is, this isn't supposed to be a cryptography course or anything like that, but it is important to be kind of familiar with those concepts. Typically, it's not the algorithms, the encryption algorithms that people end up breaking, because I'm sure everyone's heard of those instances where something goes wrong, right? Somebody's information gets leaked or somebody's account gets hacked or anything like that. But in those cases, most of the time, it's not the algorithms being broken. It's not the algorithms being cracked. Maybe, so like law enforcement, if they want to get access to some messages, they're probably not going to, at this moment, they're probably not going to decrypt the messages. They're going to get access to that individual's phone. Because once you open up that messaging app, you can see the messages right there in plain text. It has to be, you have to provide a clean user experience where the user isn't, it's got to be convenient for the user essentially. So, okay, we covered HTTPS, HTTP and REST, TCP. So when we go and send a message to the server, so it's just, this is the client, this is server. Think of it as like ping pong. The client goes and asks for this, something from the server, and then the server will want to send a message back. They'll acknowledge. I think I have some notes here for that. I guess not. They'll go and send messages back and forth, but what this TCP, the transport control protocol, the transmission control protocol, what that can do is it ensures that the message, once it makes it to the client back or maybe to the server, it ensures that the message is correct. So when you're sending messages, you're sending packets of information back and forth. So what can happen is you could deal with data corruption. So you go and you send a message, and that message goes from your phone to your router. And between your phone and your router, there might be an issue. There might be a connection issue, a physical barrier, or maybe between your router and the other user, there's something goes wrong. Well, what you can do is you can have acknowledges, and you can have failures essentially. So hey, I acknowledge that I got this packet, good to go. Or the message didn't come through. It didn't come through correctly, so resend it. And that's where it can really serve as a strong tool, basically. You don't really see this, right? So this kind of happens in the background, but it's a really, really important system for this communication. Because what can happen is, say you go and request something from the server, the client here, you go and request a resource from the server. And you just pass in for ID 300. For ID 300, we want to get something. We want to get the information for user ID 300. And something goes wrong on the way there, and now this user ID 300 turns into user ID 30. We need to make sure that this is caught. We need to make sure that the server doesn't return stuff for user ID 30. Because if you're only authorized to view information for user ID 300, there's the obvious problem. So what we can do is we can use what's known as cyclic redundancy checks. And these cyclic redundancy checks, what you do basically, and I didn't study cyclic redundancy checks super in detail, but basically it's just a method for taking that data, you throw it through some algorithm, and you send that as well with that data, and then the server goes and does that algorithm to that data again. Okay, we took the data, we put it through a cyclic redundancy check function or method, and oh look, the output isn't the same as what we sent with it. That means that the data is junk. So you need to go and request that data or not use it essentially. That's what TCP is. And then the OSI model, of course, it's kind of the layers of technology. Application layer is HTTP and REST. TCP is our transport layer 4. So 7 application layer, HTTP and REST, and then TCP is 4 transport. And then HTTPS takes a whole bunch of stuff, puts it together. And then our APIs, of course. So now that we've kind of covered all the groundwork for transferring this data back and forth, we need to cover the data itself, right, and how we're going to structure it. So this data, let's start off with objects. So I like to relate everything to the database. So say we have a couple tables here, and this is our table customer. And what might a customer, let's think of something that they might have. Customer might have devices, and we might also have logins. So the customer table might have a cust ID, and that's just their primary key. And device is going to have a device key or a device ID. This device is going to be specific to a customer, so this is going to have a cust ID foreign key, so it's K foreign key cust ID. Right, and then we I'm not going to worry too much about the one-to-many references and all that stuff there, but then our logins, we could have ID and a cust ID here for a certain customer. Honestly, maybe users might have been a better one, but whatever. So, this foreign key would go here. So, we want to get some of this data back and forth, right? We might want to get some customer information or some device information. So, this is the database, right? So this is what's storing that information. So what might be stored in there would be like for customer, that customer table. It's going to be it's not going to be clean, but I guess the point is just to understand kind of the structure. ID. And then our name. Probably can't even read that, but that's fine. And our description. So C, D, E, F, U, S, T, U, V, description, I don't know, C, D, just for some dummy information. And this is what we want to send back to the device, right? So this is what we're going to end up this information needs to be relayed back to the client, whoever requests this information. The login info, right? We might use this for authentication. So here you might have a password and a username. So you might have that other table over here. Not really gonna draw it out, just know that there's some data in there. And our devices. So say we want to go and access customer information. We have our tables, our database tables, and the data is inside of the database. It's stored in the server, or in the cloud, or on premises somewhere. We want to access some of this information here. So the first step when working with an API is you got to be familiar with the data, how it's structured. Really, that's the biggest thing, just how the data is structured. Once you have an idea of how that data is structured, then you can start looking into the API. So that API might have a couple, in C#, they're known as controllers. This isn't supposed to be perfect UML unified modeling language, but it's just kind of going to serve as like what they do. So your customers, customer, and then we have our devices. Get customer, delete customer. Just kind of sort that up a little bit. Delete customer. Expand this actually. Update customer ID and delete customer ID. Then devices, again, get devices. Update devices. Same deal as here, right, with an ID. It's terrible, I know it's not clean, but that's not too big of a deal. So this API might have this controller, right, customer controller. So you would go HTTP API / I'll just start a new line over here, get customer. D equals 3. So when we go and send this GET request here, we go and send this from the client. We send this GET request to the server will go, and in this case, for this API, it'll get the customer for that ID, and it'll return that customer information. If you want to update the customer, you could do a post request with the customer ID and then the fields that we want to update. Same with devices, so on and so forth. But typically it's handled in that manner where there's something for a certain table. The customer table might have a customer controller, device table might have a device controller. Pretty common to see those kinds of things. So let's kind of go over how this data moves back and forth. We go and send a request to this API, the server. Client here, it's probably like the 4th or 5th time that I've drawn this here. We have our user, we have our server, client server, and the client wants to go and send a request to the server. And honestly, I should go over status codes as well. Some notes on status codes as well here. And basically it's, when you go and send a request to the server, you typically get a status code back. So like 200 level status code, like 200 would be okay. 201, I believe, is created. So you created something and it was created successfully. 300 level is redirection. So a permanent redirect is 301. Temporary redirect is 302. Not modified is 304. Client error, which means that something went wrong on this side, would be unauthorized 401. This is a common one. So if you go and try to access a resource from the server, from the API, and you don't have the authorization, so you didn't send the right token, because typically, well, I shouldn't say typically, but sometimes APIs will use what's known as a token to authenticate the user. So for example, the user might go and make an initial login call to the API. They're going to try to log in for a username and a password. With the username and a password, the server is going to go check the database, maybe decrypt or sorry. So hashing, we're going to kind of go over that here because this is something that you should do if you ever create an API with authentication. So you have that username that's sent in plain text. That's totally fine. The user they might send that username. They also might take that password, and what they should do is they should hash it. So password pwd123, that goes into a hashing function, and the output is a bunch of stuff, just a bunch of text that's, you can't read it. So what you can do is you can go and have that database and you store the hash, right? You store this hash in the database, and then when the server gets that login request, they take the username, they say, okay, for this username, check the database table, like logins. Okay, we have the password here, but the password stored in the database should be plain text. Of course, we already went over that. It leads to some pretty big problems where a lot of people reuse their passwords, password 1, password 123, that kind of stuff. They're super common passwords. So what you can do though, is you can store that hash in place of that password. And what you do is you go and you take the password that the user sent and you hash it, again, using the same hash function. Very important. So you can't take like a SHA-256 hash function, and you can't try to hash it using SHA-256 on the user side and then try to hash it again using some other method. So like MD5, that's outdated, don't use MD5, but you could do that and it's not gonna work. You have to use the same hash function on both sides. So you take the password on the user side, send the hash. So the request might look like username ABC and password, the hash, all this junk, just a long string of characters. And then on the server side, they take that username, they go and look in the database, they say, okay, we found it, there's a user there, or maybe the user's not there. And then you just say, hey, it's a bad request. So you do, let's see here, 404 maybe. We couldn't find it, we couldn't find anything for that, or 401, unauthorized. We weren't able to authorize the user, whatever. But if it is there, and we get that hash that's stored in the database, we take that hash, we store it in a variable, and then we take the password that they sent, and we take that hash and compare it to the one that's stored. Oh, they're equal? Cool. Then we've successfully authenticated them. So that's something you can do also with that. Where was I though? Kind of get back into, all right, we went through that, through hashing, access that resource. Let's go over how we store that data though. So we send that message over to the server, or that request over to the server. So how do we actually transfer that data? Well, that payload, typically in an object-oriented programming language, so for example, Java or C#, you're gonna have like a class that represents it. So public class login. And then this public class login is going to have a string username, and a string password, and constructor, whatever. So we have this, and this is, I like to refer to them as object models because they represent what we're sending back and forth. So this login might be whatever, that database table, if we have that login database table. It's going to have, for example, the username and password. That's what these represent. I always like to relate it to that. So if your database table is login, for example, and you have a username and a password, that's what the class might look like. Really important. So we have this object model, and this is what we're going to use in our code. So we want to send this request to the user, or to the server, I mean. So when we send this request to the server, we have a couple options of how we can send that data. We can send it as JSON, so JSON, JavaScript object notation. So what that looks like is like this. Have really bad curly brackets, but we might have like user, and then a colon, and then that's the data. So this is the variable name, and then that's the data, password, and this here information, this is what's sent back and forth. In reality, it's serialized, and we'll kind of get into that in a little bit. But this is the information that's sent back and forth. This is how it's kind of structured. But this is not too useful in an actual programming language because this essentially is just a dictionary, right? Key value pair. So this is our key, this is our value. So we need to actually be able to use that. So what we can do is we can deserialize it and serialize it. So if we have our, let's say we have our class users, so, or not, our class login. So we have an instance of login. We have an instance of login here. And we have some JSON with that login information. What we could do is we could populate, well, we don't have this yet. We're going to go and send the request to the server. We need to populate that login variable because this login, remember, this login variable has two properties, user and password. And remember, the login variable, the type is of type login, so class login. It's going to have the two strings there. So we populate it. So login.user is equal to ABC. login.password is equal to whatever the password is. And in order to convert this into JSON, we would have to serialize it. Now, that's not a very good example when I say serialize it in JSON, because what serialization does is it takes this object model and then it also escapes it. So it might look like password. Good, password's not ABC, or the password is. And another new line. This is what would be stored. Now, I'll just use a single quote. Let's just assume like JavaScript, or you can have a single quote and all this other stuff with like strings inside of it, so double quotes inside of the single quotes. This is what would be sent, right? So this is the payload that would be sent. This is a serialized string, and all you would do to serialize is you typically have some sort of serialization function. So you'd be like serializer serialize login, and this would be assigned to some string JSON payload. I have enough space there, so get rid of this here stuff. So we have a string payload, and this is assigned whatever the value of login is when it's serialized, which would be this. That's what gets sent to the server. So what we can do once that gets serialized is on the server side, we have to deserialize it. So we take that JSON, that serialized JSON, and we would do the whole operation backwards. Now, it's important that we have that class login on the server side as well, so that we can know what to deserialize it to. So on our server side, we might do login is equal to, and let's say that the that serialized string came in through here, so let's just call it string input is equal to get input. Let's just kind of assume that that's what that would look like. Of course, if it was like in C#, you would read whatever gets passed in from that route, from that method that corresponds with your API route. But you have that class, right? So that object model, and then you have the instance of it, so login, and then you would go and deserialize it. So typically the way that would work is serializer, and it wouldn't be serializer, I'm just making it up. It's JSON converts, a popular one in C#. But typically a lot of these API systems have stuff in place already. So serializer dot deserialize. I think you have to specify a type usually, so login. And then you have to pass in that input. And then that's how you would get that. Now, if this breaks, if you passed in junk JSON or a junk serialized string, or say you don't pass in all the necessary stuff, or maybe you have like a v1 login with some login properties, with 2 login properties, and then you have a new login, so like a v2 login with properties like user1 and pwd1. This isn't going to work. It's going to break, so that's pretty important to have that consistent on both sides. But yeah, that's how you would, once you have this, you would be able to read it on the client and on the server side. So yeah, I guess we covered a bunch of stuff, but really that's all it is really. So it's just that communication protocol, and you gotta be mindful of all those items. So HTTP, REST, HTTPS, how the API works. The biggest thing is just to be familiar with what you're accessing, so what's being stored, uh, how it's structured, what the server is expecting. You can do that with you can do that typically with a route map and stuff like that. So that's about it. That's APIs in a gist. I tried to cover a whole bunch of stuff in a short period of time, but that's about it. Thanks for watching.